Welcome to The Curious Machine. Today, we're embarking on, well, an incredible deep dive into humanity's future, our insatiable need for energy, and a mega project so grand it could literally encase our very own star. Just imagine for a moment what would happen if our progress wasn't limited by the energy we can gather here on Earth. Think about the incredible feats of science, of engineering that could suddenly become possible.
It's truly mind-boggling when you start to consider the sheer scale of energy we're actually talking about here. Our sun, for instance, it showers the cosmos with an astonishing 383 septillion joules of energy every single second.
Wow, septillion.
Yeah.
That's hard to even picture.
It is. And to put that into perspective, if we could capture all of it, all that energy, we could power something like 336 million quadrillion families.
Nearly quadrillion.
Yeah, it's basically like powering 42 trillion Earths. And right now, today, we only use a tiny, tiny fraction of the sunlight that even reaches our own planet.
That incredible scale you just described, it really makes you wonder, how do we even begin to categorize civilizations by their energy appetite? Right. And that's exactly where the Kardashev scale comes in, isn't it? It's this fascinating concept scientists use to imagine how civilizations might evolve based on their energy use,
Yeah.
classifying them into types.
Exactly. And based on those calculations, we're currently hovering around, well, what some figure is a type 0.72 civilization.
0.72.
Yeah.
So not even type I yet.
No, not yet. It's kind of a testament to how far we still have to go just to fully harness our own planet's energy, let alone anything beyond that.
So for 0.72, what defines the others?
Well, from that perspective, a type I civilization would be one that controls all the energy available on its home planet. Think weather control, geothermal, fusion, everything.
Okay.
Then a Type 2 civilization could capture all the energy output from its home star. That's where we start talking about these megastructures.
Was Dyson Sphere idea.
Precisely. And then a Type 3 civilization would command the energy of an entire galaxy. Just unimaginable power.
Which brings up a crucial point, I think.
Mm.
Why this seemingly insatiable thirst for power? Why do we need so much energy?
That's a really good question. You look at our most advanced endeavors, right? Building powerful space telescopes like Hubble and James Webb.
Or things like the Large Hadron Collider.
Exactly. Constructing particle accelerators to unlock the universe's secrets, or even running modern technologies like, say, blockchain. They all demand vast amounts of energy.
And it feels like current consumption levels are really starting to put limits on our biggest ambitions, doesn't it? We're hitting bottlenecks.
We are. The very act of knowing more, of connecting more, seems to demand exponentially more power. It pushes us towards limits that Earth alone probably can't sustain indefinitely.
And this is where the idea of a Dyson Sphere comes into play.
Yeah.
This hypothetical megastructure capable of capturing a star's entire energy output.
And it's interesting, the concept was first imagined actually by a science fiction writer, Olaf Stapledon, way back in 1937.
Oh, I didn't know that. I thought it was Freeman Dyson.
Well, the physicist Freeman Dyson formally explored it later in 1960. But, and this is important, he didn't propose it as like a concrete blueprint for building one.
It was more of a thought experiment, a way to consider how really advanced civilizations might operate, and perhaps crucially, how we might even detect them from afar.
Now, when people hear Dyson Sphere, I think they often picture, a giant solid shell completely surrounding a star, like something out of Star Trek.
That's the common image, yeah.
Yeah.
But that's actually not what scientists, including Dyson himself, really envisioned as practical. A solid shell is, well, it's pretty much mechanically impossible for several reasons.
Like what?
Well, for one, just the materials. You'd need more material than exists in our entire inner solar system just to build the thing.
Wow. Okay.
And it would need to be incredibly far from the sun, too. Otherwise, it would just, melt.
Right. But there's more, isn't there? Something about stability.
Yes, exactly. Even more critically, a solid sphere would be inherently unstable. Basic physics, Newton's laws actually show us that inside a hollow sphere, gravity pulls equally in all directions from the shell itself.
So there's nothing holding the star in the center. Nothing from the shell, no. So even a slight nudge, a slight shift of the star off-center, and the gravitational attraction to the closer side would pull it in, leading to a catastrophic collapse. Boom.
Yikes.
Plus, stars themselves aren't perfectly still. They wobble as they move through the galaxy, and they change in size as they age. A fixed, solid structure just wouldn't work long term.
Okay, so if not a solid shell, then what is the plausible vision? What did Dyson and others actually have in mind?
This is where the ideas get really ingenious, I think. The more plausible concept is what's called a Dyson swarm.
A swarm, like bees.
Sort of. Think of it more like Elon Musk's Starlink constellation, but just on a truly massive, massive scale around the sun.
Okay.
It would be made up of millions, maybe billions, of independent solar panels or energy collectors, each orbiting the star on its own path.
So like a cloud of orbiting power stations.
Pretty much. And these panels, they'd likely communicate with each other, maybe adjusting their positions, their orbits, to capture the maximum amount of energy and avoid collisions.
That sounds complex, but maybe achievable eventually. Are there other ideas?
There's another neat variation called a Dyson bubble.
Bubble?
Yeah. In this design, each individual solar panel or unit would be basically a static satellite.
Static. How does it stay up against gravity then?
It uses the sun's own radiation pressure, the solar wind, like a light sail. The outward push from the sunlight and solar wind perfectly balances the inward pull of the sun's gravity, keeping it hovering in place.
Wow, okay, so using the star's own power to keep the collectors in place? That's clever.
It's quite remarkable, yeah, using natural forces to maintain such an immense structure.
So if the what is maybe a swarm or a bubble, then the how? How do we even begin to build something on that scale? I mean, the International Space Station, which is our most complex, most expensive mega project ever.
It'd be like playing with Lego bricks next to building a Dyson Swarm. Absolutely dwarf it.
So you could build it on Earth and launch it whole, obviously.
No way. The pieces, the individual collectors or swarm elements, they would need to be manufactured and assembled in space, much like the ISS was built, piece by piece, module by module over many years, but on an exponentially larger scale.
Okay, assembly in space.
Hmm.
But the materials.
Yeah.
Where do we get the materials for billions of solar panels or statites? That's an astronomical amount of stuff.
It really is. And that leads to some pretty radical ideas. One prominent one is to literally dismantle an entire planet.
Dismantle a planet. Syria.
Seriously. Like Mercury, for instance.
Mercury. Why Mercury?
Well, think about it. It's very close to the sun, which is convenient for building something around the sun. It has relatively low gravity, making it easier to launch materials off its surface. And crucially, it has no atmosphere to create drag or interfere with launching. It's almost like a perfect pre-packaged quarry of raw materials right where you need them.
So you'd set up what, robot factories on Mercury?
Essentially, yeah. Automated systems, maybe self-replicating machines that would mine the planet, process its mass, convert it into solar panels or swarm components.
And then launch them into orbit around the sun. How? Not with rockets, surely, for billions of pieces.
Probably not conventional rockets, no. The energy cost would be immense. Theorists propose using something like a space gun, or more accurately, an electromagnetic mass driver.
A space gun.
Not for destruction. Think of it like a giant, high-speed electromagnetic rail system. It would accelerate the components, the panels, to escape velocity and literally hurl them off the planet into their designated orbits.
That just completely changes how you think about planets like Mercury, doesn't it?
Right.
From just a dot in the sky to a potential resource depot for humanity's grandest project.
It does. But let's be clear, this isn't happening next week. A project like this would take centuries, maybe even millennia.
And it would require unprecedented global cooperation, economic stability, political stability. Things we're not exactly famous for as a species.
That might be the biggest challenge of all, honestly. The social and political hurdles could be even harder than the engineering ones.
Okay, let's say, hypothetically, centuries from now, we manage it. We have this swarm collecting unimaginable energy. How do you get all that power back to Earth or wherever it's needed?
Another huge engineering puzzle. The most plausible proposals involve using highly focused beams, either powerful lasers or microwave beams.
Beaming energy across space.
Oh, yeah. Transmitting the energy, potentially almost loss-free if done right, across the vast distances of the solar system.
Which would mean what on the receiving end?
You'd need absolutely massive receiving stations on Earth, or perhaps on the moon, or orbiting stations. Giant antennas, essentially, to capture the microwave or laser energy and convert it back into usable electricity. And then you'd need a completely redesigned planetary grid to distribute that immense power.
It's just layer upon layer of technological marvels needed. But you mentioned earlier that Dyson's original idea wasn't just about energy for us, right? It was about detecting others.
Exactly. That was a key part of his 1960 paper. Freeman Dyson proposed that such a massive structure, while capturing visible light, would have to radiate waste heat. lots of it.
As infrared radiation.
Precisely. So, detecting a star that's unusually dim in visible light but glows brightly in infrared could be a technosignature, a signpost of advanced extraterrestrial intelligence that has built such a structure.
And scientists are actually looking for these signatures now.
They are, yeah. It's part of the broader search for extraterrestrial intelligence, SETI, looking for anomalies that physics as we know it can't easily explain.
Wasn't there a star a few years back that caused some excitement? Tabby star.
That's the famous one, yes. Pre-IC 8462852, or Tabby star. It showed these really unusual, deep, and non-periodic dimming patterns. For a while, an alien megastructure, maybe a Dyson Swarm under construction, was floated as a possibility.
But it turned out to be something else.
The consensus now points towards large clouds of cosmic dust as the most likely explanation. But it definitely sparked a lot of interest and showed that we were capable of detecting such strange stellar behavior.
Are there other candidates?
There have been more recent surveys looking specifically for excess infrared radiation, particularly around M-dwarf stars, which are smaller and cooler than our sun. Some potential candidates within about 1,000 light years have been flagged, but scientists are very cautious, rightly so, about jumping to conclusions. There are many natural phenomena that could potentially mimic that signature.
Still, the possibility is out there. And searching for these megastructures is essentially how we might look for those Type 2 or even Type 3 Kardashev civilizations across the galaxy, right?
Exactly. It's one of the few potentially detectable signs of really advanced engineering on a cosmic scale.
Thinking about the Kardashev scale again, it also makes you consider the fate of civilizations, doesn't it? As we progress, if we progress towards Type I and beyond.
There's a concern, yeah. The idea of Malthusian catastrophes that our energy consumption and population might grow faster than our home planet can sustain.
Leading to a kind of critical bottleneck, a period with a really high risk of self-destruction before we can make that leap to becoming spacefaring or harnessing the star.
Some thinkers definitely see it this way. It makes you wonder if maybe that's an answer to the Fermi paradox, why we don't see signs of advanced life. Perhaps many civilizations hit this great filter and don't make it through.
Or maybe they change.
That's another line of thought. Maybe advanced civilizations don't just keep scaling up physically. Perhaps they transition beyond biological forms entirely.
Into what? Digitized civilizations, living in simulations.
Possibly. Or maybe they find ways to manipulate space-time itself, transcending our current understanding of the universe altogether. Or perhaps the drive isn't always bigger, faster, stronger.
What do you mean?
Maybe the path forward is miniaturization, making technology incredibly powerful, but incredibly small and efficient, removing the need for such vast macro-scale energy collection in the first place. Their development path might just look completely different from what the Kardashev scale predicts, less visible to us.
That's a fascinating thought. So they might be out there, just subtle.
Or operating on principles we haven't even conceived of yet.
Wow. This whole deep dive into Dyson spheres and the Kardashev scale, it really does push the boundaries of our imagination, doesn't it?
It absolutely does.
It's such a powerful reminder that while these concepts are, hypothetical for us right now, they are grounded in our current understanding of physics, and they reflect the potential trajectory of our own technological needs, which seem to be growing exponentially.
And whether we ever actually build one or if we ever encounter a civilization that has just contemplating these possibilities, I think it helps us understand our own place in the cosmos. It frames the immense challenges, but also the opportunities that might lie ahead.
It really does. And it leaves us with that profound question you touched on. If truly advanced civilizations are out there, why the silence? Is it because they tend to self-destruct before reaching that galactic scale?
Or have they simply transcended, moved on to a level of existence or communication that we just can't detect or even fathom yet?
Makes you think, what do you think our next great leap will be? Where are we headed on that scale? Thank you very much for sharing this enjoyable conversation with us. Until we meet again tomorrow with a brand new topic, take very good care of yourselves. Goodbye.